tension because we're given the acceleration. Normally you'd be looking for the acceleration, but this time because we're given it, we're just going to solve for tension. So it means the tension then is going to equal ma plus fg. And of course fg is mg, right? So it's mg. So that means my tension, I can rewrite it as the mass times the acceleration plus g. Okay? And we said 1.8 meters per second?
Yeah.
Okay, so this is 200 kilograms, right, times 1.8 plus 9.8. Okay, so what is that, 11.6, right? So 11.6, 23.2, and then 1, 2, right? So
Okay. Had the acceleration been going down, would you do t equals m a
if the
minus g?
acceleration was going down, we chose this is positive, then we would have put a negative sign there, which would have translated to a negative sign here, negative sign there,
Okay.
and then this would have been a negative sign. So instead of a 23, it'd be,
Okay. Cool.
less than 1,800.
If it says, like you put like some y goes that way, do we have to put that or?
No, this is not required for the free body diagram. I'm just using this so you guys understand my rationale for choosing this positive and this negative. I could have just as easily taken this as positive and these two as negative. It's arbitrary. I'm just saying, hey guys, I'm choosing up as positive.
So if you solve the actual equation, would you just think you know our y's going that way? Or
I'm
you don't even
choosing the
care?
signs of these guys based on some reference. And that reference is up to you, right? So if I choose up as positive, then obviously t is positive and this is negative and this is positive. If I choose down as positive, then this is negative and this is positive and this is negative. Because it's saying it's accelerating upwards, but
You're choosing a middle.
so in the end, the equation is going to be the same. You just, because you'll end up with negative, positive, negative, and then when you get rid of the negatives, it's the same exact equation. Right?
Yeah.
Why do you have to factor out the mass?
I don't. I'm just. I mean, algebra thing is like hard coded. You don't have to. You could have plugged it in. I mean, once you got to this point, you could just plug in the numbers, right? I do this because in the other class as well, you get to this equation, it doesn't change, but then we say, okay, in one case it's 1.5 or 1.8, in the other case it's negative 5.6. So you start from this point and then you just have 2, 1, 2, and it's a little easier to do. But this one you're only asked for 1 in this one, I'm pretty sure. But if you're asked for 2, you guys know how to do it. It's just changing the value of a, right? Okay? Clear? This is the easy problem. This is the gimme, pretty much. So
How would you change that up on our circle exam if you would choose?
that's what I said. Like maybe I change the value of a to a negative. Right? This is old. I gotta have this for so long. Okay. Onward and upward. That's really what I said, right? You know when you push the red button? No? In the glass elevator?
Somebody came.
You tell them we're just finishing up, okay? Alright, kilograms. And it's being pulled with a force of 40 newtons. And the angle the pulling is making, and the angle is what, 60 degrees? Yes. Let's assume this is the x direction. Okay? So, in this problem, I think initially there's no friction, right? So, in this problem, what you want to do is you want to identify all the forces. I mean, that's the first thing you want to do. And that's why you do a free body diagram, is because it helps you do that. So, if I look at the forces, and I realize that this is going to take an x component of forces and a y, then I'll break it up in x and y parts. So, this part here I can say, oh, well, this is my FPX, right? I can say this is my FPY. Now if I look at this right away, you understand that this is the same as putting my FPY here.
Yeah.
Okay, so you guys remember adjacent, opposite, so this would be my cosine and sine parts, right? Then we're gonna have the force of gravity pulling down the box, right? And we're gonna have the normal force up in the box. Okay? And if possible, right, we're gonna have force of friction, but we don't know if there's any friction. I mean, at this point, there's no friction. So once we've done the free body diagram, it's easy for us just to look at and decide how to do the sum of all forces. Let's see, I use a purple color. So when you're doing this kind of problem, you don't have an issue understanding what's positive and what's negative, right?
Yeah.
Because you can see, right? I mean, you choose this is X and maybe this is Y, right?
Mm-hmm.
So from there, it's easy for you to figure out who's positive and who's negative?
Yes.
Okay, so it's only when you're doing like projectile motion or free fall, okay. Okay, so in this case, let's start with the Y part. So the sum of all forces in the Y direction, right? This is gonna be, we see the normal force, we see force in Y, pulling Y, right? And we see Fg, so normal force plus the pulling force in the Y direction, right? Minus Fg, okay? Because Fg is going down. Now we don't expect it to leave the ground, we don't expect it to cut through the ground, so this whole thing is going to equal 0. So that means we can write this as the normal force equals Fg minus the pulling force in the Y direction. This would only be important to us if we were actually calculating something about the friction. Like we're given the coefficient of friction, we wanted to calculate the total friction force, or we're given the friction force, and we wanted to find out what the coefficient of friction is, that kind of thing. So we're not doing that explicitly right now. We'll probably do that for the next test, but nonetheless, it gives you a sense of how to do it. The second part is the sum of forces in the X direction. Okay. Now, if we assume this is positive X, there's only one force in the positive X direction, which is our pulling force in the X direction. There's nothing balancing it, right?
Mm-hmm.
So we imagine it's going to accelerate, right? Yeah?
Mm-hmm.
I mean, according to Newton's second law, if it's an unbalanced force, we see an acceleration. Yeah? So, and then of course we can solve this. AX is FPX over the mass. Okay, now we haven't calculated what FPX and FPY are yet, but we do know the angle. So, I don't think I can fit it. So FPX is going to be FP, which is the hypotenuse, right? Times the cosine of the 60 degrees. Okay, cosine 60 is half, and FP is 40, so that means this is going to be 1/2 of 40 divided by, and the mass is 20 kilograms. So 20 divided by 20 is meter per second squared. Right? Okay, so we know the acceleration in the X direction is going to be 1 meter per second squared. Okay, you see that? Now, of course, you're going to verify this in the calculator that cosine 60 is 1/2. But I just skipped ahead. So he's hanging out with you. He's very talkative. I always thought he was really quiet.
What?
I noticed that. I noticed it.
Me?
Yeah.
Oh.
He's usually so quiet. It's like,
No, I'm usually quiet with like people I don't really know.
hmm.
So.
Yeah, we're cool now, so it's fine.
I see how it is. Huh? You're not quiet. Rahul's told me the truth now. I know all about it.
In the red, what does FP equal to again? It's a little hard to read that.
This, in the red,
In the red, yeah.
it's 40, and that's what the question gives you, is 40 newtons.
Or 40 newtons, not bad, 40 newtons, not bad.
Well, it's not bad. It's a given.
Oh, alright, thank you.
Alright, so I understood that the sum of forces in the Y
This one is-
direction.
Yeah.
The reason why it equals out to 0, I understand the forces balance out, equal out, right? But that's because when we're pulling at 60 degrees, you said we're not expecting it to go up, right? That's the whole like concept behind it. We're not expecting it to accelerate in upward direction.
Yeah. So, if you can pull it straight across the floor, right?
Yeah.
But I can also pull it at 60 degrees. It's not going anywhere.
Okay.
It's not leaving the ground. But I could jerk it.
Yeah. So
Like
if it's
jerk
a
it.
strong enough acceleration, or
Yeah, so it's possible to jerk it
yeah.
so you'd have strong enough acceleration to leave the ground. But
Okay.
that would mean that you know, the Fy component has to be greater than gravity.
Yeah.
Significantly greater than gravity, right?
Uh huh. Okay. Yeah.
Because then the normal force would be 0 or.
Mhm.
Okay. I mean, as a matter of fact, if you take a calculator and you calculate 20 times the sine of 60, what do you get?
Who's a sine or cosine?
Yeah, sine of 60 degrees times 20,
17.3.
17.3, right?
Mhm.
And the mass of this is, right?
Yeah.
So it's only 17.3 newtons, but this thing is 20 times 9.8,
Yeah.
right?
Mhm.
So it's like 10% of its weight. So you're nowhere near. Yeah. So I could ask you an extra question. Hey,
Yeah.
well, how much force
Is
does it have to be pulled to leave the ground?
Okay.
Yeah. And then he'd be, oh, why would I do it?
How would you do that again?
You just find that this FPY has to be bigger than gravity. That's all. So if you know gravity, you know its weight, and you know that part of it. So it would be, so in that context, you'd have, if you looked at it like this, you'd have mg, right, which is gravity. In this case, has to be equal to or greater than. Oh, let's just say greater than, right? This FPY. Well, FPY is FP times the sine, right, of 60 degrees.
Mhm.
So we just say FP then, so we'd say mg divided by the sine, right, of 60 degrees equals FP, or is, I'm sorry, this is going to be this way. So at 40 newtons, we know it's nowhere near, right? But maybe 400 newtons,
Mhm.
right? You got it? And that's FP, by the way. Sorry, messy. Okay, so the next, so I erase this part? Yeah?
Mm-hmm.
Yes.
The next,
What did we need the sum of y forces for?
for your education. If I had said later on, by the way, I want you to calculate the coefficient of friction.
Mhm.
The way you do it is, you remember that the force of friction equals the coefficient of friction times the normal force, right? So if I say to you the friction is 4 newtons, and now you know what the normal force is, then you can tell me what the coefficient of friction is. Typically, if you have something sliding and there's any friction discussion, it's a good idea in your mind to think, I want to know what that normal force is,
Mhm.
because that's how they're related. They're related to each other. Whether or not it's asked for, it's a different thing.
With the frictional force, wouldn't it be negative in this instance?
Well, the direction is negative. The force itself is a number, right?
Right,
And it's being pulled in the opposite direction.
so the number itself would be negative?
No, the number, so when we say the frictional force will be 4 newtons.
Okay.
But when we add it to this sum, right? When we add it to this sum here, it's going to be in the negative direction. So the reason it's negative is the direction, not the number, because it's going in the opposite direction. It's resistant. So air resistance and friction are always resistive forces. So that means that they're always in the opposite direction of motion. So in that context, if you're using the reference of motion, the direction of motion as your positive, then it's always going to be a negative. Is that true?
Yeah.
And the normal force is always perpendicular to whatever is you have, right?
The normal force is perpendicular, but like we said, frictional force is proportional to the normal force. And like we said in class, if we're pushing this along, it's no big deal. But if we're pushing down on it and then trying to push it, it's going to be harder to push, right?
Yep.
Well, but that pushing down is related to your normal force.
Mhm.
So as you increase your normal force, it's going to be harder to push, so it increases your friction.
Okay.
So that means you have a natural coefficient of friction, which is really a measure of roughness between the materials or stickiness
Mhm.
of the materials, and then you have how much weight behind it is, that you have to.
Okay.
Okay? Okay, we're good? So,
Wait, can you explain, sorry. You lost me on how you're actually calculating
Well, in this problem, I give you a frictional force. If I was to calculate the frictional force, right, the definition of frictional force is the coefficient of friction times the normal force. So, right now, I know Fg, right? I know my normal force, don't I? I know Fg, which is mg, and I know Fpy, which we said was like 17 or something. And you guys calculated it on the calculator. So, we know, 196 minus 17, right? That'll be a normal force. You alright?
Okay.
Are you in pain? No, she made a grimace with her face, so I just got worried for a second. Okay, so we know that this is like, 185 or 184, no, 179 newtons.
Okay.
How did I do that? Okay. So this is coefficient of friction times Fg, right, which is 196, okay, newtons, minus, we say 17, even?
17.3.
17.3. Okay, so this will be 82.7, 182.7. No,
178.7.
178.7, yeah. Because it's, okay, so it's 178.7. Now, I'm not saying I'm going to do this to you in the test. I'm just, later on, you're going to have to be able to understand it in the next step. But the fact is, you asked why I grabbed the n. Well, I grabbed the n because I'm used to doing it because I know it's part of a bigger problem, and I like to have you use like the general steps, and then you guys decide what you're going to take from it. Does that make sense? Okay. But right now, even this problem, I gave you the force of friction, and you can calculate the normal force. So even for this problem, you could actually tell me what the coefficient of friction is, right? Because you could just say, the coefficient of friction is going to be the frictional force divided by the normal force. And it's going to be a small number, right? It's like 4 newtons divided by 178. Pretty small. And usually, 0.05, 0.04 kind of thing. And it has no units, by the way. The coefficient of friction. Okay, we're good.
Will we have to do this for this exam? Like, will we have to find friction for this exam?
The test question is probably getting pretty close to your test question, as it is right now.
Well, what does the coefficient of friction describe?
Yeah.
So,
It's like
different materials are more abrasive or less abrasive or more sticky than other materials, right? So coefficient of friction takes into account the material factor, whereas the N only takes into account how much weight is behind, pushing down on it. So different material, like Velcro has a very high coefficient of friction, right? But if you do like a baby powder on something smooth, it's
Does friction have units?
the coefficient of friction doesn't have units. Coefficient of friction is you have the static friction and dynamic friction, right? But they're unitless. It's a unitless constant. But the force of friction is newtons. It's a force.
Right.
And normal force is newtons. It's a force. So newtons and newtons. So this one can't have coefficients. Good. Okay. So to finish this problem out, which is, I say, okay, now there's friction. So we just have to rewrite this equation right here. So this is part 1, right? So for part 2, we say the sum of all forces in the x direction. And this is now going to be, the pulling force is positive in the x direction, so it's Fpx, minus force of friction, which is going in the opposite direction, right? So it's a force of friction. Okay? And like we said last time, we expect there's going to be acceleration. Unless the friction is so high, right, it won't move, but we'll find that out. Because if these are equal, then this will be 0, and we'll find out that Ax is 0. So it's safe to put the x in the beginning and then find out it's equal to 0. Okay? And we want to solve this for a, so we're basically just going to divide both sides by m. So we're left with Ax equals Bx minus the force of friction over m. Okay? And Fpx is 20, so this is going to be 20 minus 4 over 20, right, which is 0.8 meters. So you notice because there is friction, the acceleration that took place is different, right? It got less. Okay? It makes sense, right? If you got a bigger number, whenever you do these kind of problems, look at the answer and ask yourself, does it make sense? Because if this was a bigger number, we'd be like, wait a second, adding friction, I shouldn't get more acceleration. Okay. That's it. I mean, the problems, I don't think it's a very hard one. I mean, this part, you're right. You know, you don't necessarily have to write it down to answer the question, the requested question. But if I were to, you know, God forbid, say, what's the coefficient of friction, then you need that step. I know she's trying to figure out, okay, what's he going to do to us in the test again? Now that he mentioned it, you know, okay, whatever. It's all good. I wouldn't worry too much about it. Okay, so we're good? No more questions?
Short answer number 4.
Wait, on this.
Oh, on that. Oh, oops. Sorry.
Okay, so we're good? Soccer ball. It's going to be going up with some initial speed, v0. Initial velocity. It's going to go up in the air. It's going to come down. Right? And what we want to find is, I guess, what? Time of flight, maximum height. Right? Right? We want the range, how far down the range it went. We want to know how long the flight, right? Is that right? Yep. Okay, so. Okay. So in this problem, of course, since this is a vector going this way, again, this is a two-dimensional problem, it makes it a lot easier to break it up into x and y parts. And once it's in x and y parts, we just use our regular, solve, sum of forces, solve for the acceleration, and then plug it into the equations of motion. And you just have to do it twice, right? Because there's more than one dimension. So we have the vx part, right? Vx0 part. And here we have the vy0 part. Okay? And we don't really need to know the values of that. We can calculate the values in the end, but we just recognize that that's the case. What was the angle? There's some angle here.
60.
Is it 60? Apparently I love 60 degrees in this test. Okay, and this initial speed was 25 meters a second?
Yes.
So v0, 25. Okay. Okay, so in this case, if we look at the remember when I did this last time, we broke this into two parts. And the reason we broke it into two parts is because we're going up initially, and acceleration is going down because of gravity in this part. But then when we're going down and acceleration is down, it means that the direction of acceleration changed. And since it changed, theoretically you can make this a two-part problem, right? In part 1 and part 2. But what we saw in class and what we also saw during the reviews is that if you solve for part 1, you automatically know the answer for part 2. Okay? Okay, so for part 1, first thing we're going to do is a free body diagram. Do red, maybe. Okay? So we have a body, soccer ball, and the force of gravity going down. There's no other forces acting on it. If we say there's no air resistance, Victoria, can you see? Okay. There's no air resistance. That's the only force acting on it in that direction. Are there any forces acting in the x direction? No. So that makes life really sort of simple for us, doesn't it? Sure. Okay, so if we look at the y direction first, if we say the sum of all forces in the y direction, right? It's moving in this direction, so I'm going to consider this a positive motion right now for this part of it, or direction of motion is this way. But gravity is in the opposite direction, so I can say negative Fg equals a mass times acceleration. Okay? Now, if I divide, or in the y direction, if I divide by m on both sides, I have my acceleration in the y direction, right? So ay equals minus Fg over m, which equals minus g. Okay? Fg is always mg, so m's cancel, and I'm left with negative g. And in the x direction, so forces in the x direction, well, there are no forces in the x direction, right? Which is max, and this implies that ax equals 0. Okay? That's it. So we don't have to worry about acceleration in the x direction. Okay, so now we have two sets of problems. Remember, we free body diagram, sum of forces, and then equations of motion. So if we treat the equations of motion first for the y direction, right? So remember, step A, step B, step C. So now, and then solving for acceleration. Now we plug in the equation of motion. For y, we're going to say Vy final equals Vy0 plus AT, right? We're going to say y final equals y0 plus Vy0 times time plus 1/2 AT squared. So, what do we know? Remember, when you get to this stage, you ask yourself, what do you know? Because you know your equation that you know, it's determinable. In other words, I know everything but one unknown. And with just one unknown, I can solve this equation, either this one or this one. And that's how you determine the first one you're going to use. So in this problem, we have two things. We know at this point the maximum height. Remember what we did in the lab. What's the speed going to be up here?
0.
0, right? Okay, so that means that V final for this point is 0. So we know this, right? We know this guy. We know the initial speed in the y direction. We know the acceleration in the y direction. Sorry, it's AY, right? AY. Because we got AY right there, right? So the only thing we don't know is time. And that'll be helpful to us because if we look over here, we don't know the final height, right? We don't know the final height and we don't know the time. So there's two things we don't know on this side. So to solve this one, we need to find the time. And this helps us do that. So we write this down. We write this as 0 equals Vy0 minus g times time. So we just plugged in the AY for this right here. And then of course we're just going to bring the GT over. So that means Vy0 equals GT times time equals Vy0 over g. And we've talked about this in class a few times where it's the initial speed over gravity. In any projectile motion, it's always going to be the case in that y direction. So we found the time to max height. So time to max height. Time to get to this point right here is the initial speed divided by the acceleration of gravity. Okay? So finding max height, find the time of max height, now we can actually find the maximum height. If we started from the ground, if y0 here is equal to 0, if we started from the ground, and that goes away, right? That means y final is going to equal Vy0 times time. And it's going to be this time right here. It's going to be this time. It took that long to get here, right? So it's times time. So we have Vy0 over g minus 1/2 g. And then t squared is just this t squared, right? Which is going to be the Vy0 squared over g squared. And we can simplify this algebra. We can get rid of one of these g's, right? Because it's g divided by g squared. Okay, and then that leaves us with Vy0 squared over g minus 1/2 Vy0 squared over g. So an apple minus half an apple leaves me half an apple, right? So equals 1/2 Vy0 squared over g. Okay. And we can solve this for a particular number. So this gives me my maximum height. This y final, this distance is my my distance, but this maximum height is my y final. Get it? This is the same location. So this is my h max. You guys understand that? That these two are the same number? That's sort of clear? Okay. I don't know who is telling me that I just all of a sudden gave you h came from nowhere. Like I pulled a rabbit out of my pocket or something. We're good. Okay, so at this point we could plug in some numbers. Vy0, I didn't leave any space to write it down. Well, anyways, Vy0 is going to be V0 times the sine, right, of whatever the angle is. Now you guys agree that that's a sine, right? Because if I move this over there, here's my adjacent, here's my opposite. So this is gonna be cosine, and that's gonna be sine, right?
Thank you.
Good, okay, so that means Vy zero. So Vy zero is gonna be 25 times the sine of 60 degrees over 9.8. Or the sine of 60 is 0.86.
It's gonna be 2.2.
2.2?
Yeah.
Okay, so that's the time it took to get to the top, okay? And then we can look at y final now. So y final, Victor, I'm sorry, I know I'm in the way of this one. So this is gonna be 25 times the sine of 60, all squared, right? That's squared right there, divided by 9.8. So 40, no, let's see, 25, 26, quarter 2, 4, 2,
I got 23.9.
23.9,
You're just squaring the 25 sine of 60, right? Not the whole thing.
2.9,
23.9.
23.9, yes. Yeah, that's all we're doing. See, if we look here, all that's squared is the Vy0. And Vy0 is V0 sine, so you square the whole thing. And I know people are gonna make that mistake in their calculator.
Yeah, and square the 9.8 too.
No, no, no. See what happened here?
Yeah.
We got rid of one of this g squared because the g's cancel. There's only one g here, so there's no squared g.
Yeah.
And 1/2 isn't squared. So this gives me the height, 23.9 meters above the ground is the maximum height above the ground. So we've answered the first half of this problem. It asked, basically how high is it gonna go, and it's gonna ask how long before it hits the ground. So right now, there's a couple of things. One is, as we discussed in class and in the reviews, that the time it took to go from here to here, because it's decelerating, right? It's from its initial speed, it's decelerating till it goes to 0, and that acceleration is gravity. And from here, it's going from 0 to some final speed, and that acceleration is gravity. So since the distance is the same it's covering, then it takes the same amount of time. Makes sense, right? So as long as they're at the same level, okay? If we had a problem where we had like something on a cliff and he's firing a cannonball like that and then going to the ground, of course that's not the same level, right? So then we wouldn't be able to use that argument. And there's a homework problem, something similar to this one too, I think. Right, Luis? So the thing is, this time here is equal to that time there. So we know the time of flight is going to be 2 of these, right? So it's, I guess, 4.4. Was it 2.2 even, or was it just? It doesn't. I mean, whatever. It's whatever the number is.
It was 2.209.
0.9, so it'd be 2.21, right?
Yeah.
Okay, so then the time of flight, right, is going to be 2 times that 2.2. Okay? Which is our, whatever, our 4.4 or whatever.
1.8.
Seconds. Yeah.
What question is this again?
What question is this?
No, this is the same question, right?
This is the one that you asked?
Yes, alright, I just wanted to double check, this is part 2, right?
Actually, I think the first question it asked you is, how long is it going to be in the air?
Alright, sorry about that.
So this
No, it's all good. And then the second part says how high is it going to go. I think the last part is how far down the field.
Yes, that's right, sorry.
So right now, it's fine, don't pause, you're fine. So this is the total time of flight. So what we just calculated right now, this guy, is basically the answer to the first question. Total time of flight. And then this guy right here represents the maximum height. So it's like question A, question B, and question C I'm gonna have to erase a little bit to get to question C. Okay? So, let me do this real quick. Can I erase or? maybe?
Yes.
Okay, I'm gonna erase the y part here, because you guys would have copied that down already, in essence, if you guys are scrambling. So we know the time to max height, or actually the time of flight. Now that we know the time of flight, right? And this is gonna be 2 times this guy, right? So it's gonna be 2 times vy0 over g. We just calculated that, okay? So since the acceleration in the x direction is 0, that means what? That means that the x final, which minus equals x0 plus vx0t plus 1/2 ax t squared. Now this is the equation of distance. It's asking how far downrange. Well, this distance, or the difference between the initial position and the final position, so I can rewrite that as distance, right? Is what we're looking for. Now we have the time, we have the initial speed, we have the acceleration, so we know everything. We can just calculate it. So if I remove this over, so this is going to be my delta x now, is equal to my vx0, right? Times this time right here, 2 vy0 over g, okay? And the ax is equal to 0, yeah? So that means I can just cross that off. So this right here would be the distance down, the analytical answer for the distance downrange. It's vx0 times the time of flight, the time it took to go from here to there. Right? So can I erase this part now? Yeah. Okay. If that's the case, then it's really easy just for us to calculate it, right? So this delta x, and remember delta x is just x final minus x initial. I just moved it over there, right? It's just the distance between the initial and final location, so final position. So delta x then equals, vx0 is going to be 25, right, times the cosine of 60 degrees. That's vx0, right? Times 2 times vy0, which is 25 times the sine of 60 degrees, divided by g. Okay? Clean it up a little bit. 625, 1250, okay? 1250 divided by 9.8. That's the cosine of 60. That's the sine of 60. If that's easier for you guys to do in the calculator. Right? 625 times 2. Huh? What?
Why is it being multiplied by 2?
The time,
Oh, okay.
the time here is time of flight, is this time plus that time. And remember the times are the same. So if this time is vy0 over g, and this time is vy0 over g, then the total time is 2 vy0 over g. If this time is 5 minutes, and this time is 5 minutes, then the total time is 10 minutes, right? So that's where the 2's coming from. Now if we were only talking about the time to get from here to here, right? Then it would be just vy0 over g. But if you want the whole distance, then you're going to have to multiply by 2 anyways. No? Odyssey. In which part? On the understanding of what the time, how the time is related to x, or just the duration of time in general?
I'm confused where the cosine and sine came from.
Okay, it's alright, I'm writing it again. Don't worry, I'm writing it again, yo. Okay, so we just wrote this as delta x equals, in this case, I'm going to put 2 vx0 is vy0 over g, right? So in this picture here, we have v0 equals vx0 vy0, right? And that is supposed to be an x, okay. Now here's your angle right here. So we know that this side right here is cosine, and this side is sine, right? So that means that this Vx0 is going to be the hypotenuse V0, right, times the cosine of the angle. And the Vy0 is going to be V0 times the sine of the angle. So all I did in this part is I just plugged it in. I just plugged this in there and that one in there.
Okay.
So I just end up getting the sine of this.
Someone may have asked this already, but what's the 2 represent again?
2?
Yeah.
The 2, okay, so the time that the ball took to go from here to here, right, that time to maximum height, if you remember, the time to maximum height was equal to Vy0 over G,
Yes.
which is going to be a number. We didn't plug in the number, it's going to be a number. So that time is the time it took to go from here to here. And we recognize because they're the same acceleration, the value of acceleration is the same, that means it's just doubling the time to go all the way over. So that's why the 2 comes in.
How do you know the acceleration is the same?
Because when you throw a ball up in the air, the acceleration is 9.8 when it's going up, 9.8 when it reaches the top, and 9.8 when it falls. Remember multiple choice question.
Yeah.
So that's it. If there's air resistance, then it's a different issue. But even then, you're going to find going up and going down, there's going to be similar relationships to the speed. Okay? Are you sure? Liar, liar. Okay. So we're good then, right? I mean, basically, we just didn't plug in the numbers. So, did you guys want me to?
It's 55.23. If you wanna.
55. Okay. So the delta, the range downfield is 55.23 meters. So basically, a little over half of the soccer field. Okay. So it looks like he doesn't have much of a leg on him, even though 25 meters a second seems like a lot. You know what it is? It's because the angle's too high.
Yeah.
He was scared. Some big guy was coming rushing at him. He's like, ah! He kicked it way up.
So if the time to maximum height and the time down are equal, does that mean that that midpoint time or the X range at the midpoint at the maximum height
Exactly, would be half.
would be half?
This would be exactly half of the whole range. So that's another way you could do it. You could say, oh, well, I need the time to get here, and this is half my distance, so I just double my distance instead of doubling my time. But it's the same, right? I mean, if you look at this, right? I mean, this right here is the time,
Yep.
and this right here is my position. So I can take this whole thing will be my distance,
Mhm.
and then I just double it.
Yep.
Or I can double the time. It ends up being exactly the same.
Okay.
It's kind of off topic, but during the exam, is plug and chug necessary to get credit for? Can we just find the general formula without putting in the numbers?
You get 100% of the points if you show the work, come to the correct analytical answer, and then plug in the number, right? Derive the number from a calculator. If you just screw up with a calculator, right, or you make one stupid mistake in your algebra, you're gonna lose a point. So you keep everything else, right? That's the point. But if you just basically, look at the problem and then just plug it in your calculator and give me a wrong number, huh?
So in the end, we do have to find the number, right?
If it asks you, if it says derive the formula for acceleration, then you don't have to give me a number. But if it says, what's the speed or how long did it take, then yeah, it means that you need a number. So it's sort of on the question.
And we will have 4 short answers in the exam.
Yeah. In all honesty, so you guys are not worrying too much. I want you to worry a little bit so that you keep on studying hard, okay?
Yeah.
But it's going to look very, very similar to this test. Even the questions themselves, probably most of them will only be changing numbers.
Will we have a formula sheet, or will we have like?
The formula sheet, any formula you need will be put up on the board for you. So you just tell me. If I don't have it on the board already, you just say, what's the formula for V? What's the formula for X? The only thing I don't want to put on the board is how you break up sine and cosine. I want you guys to sort of remember that on your own.
all the questions we usually just use cosine for the x anyway. Like I was studying yesterday all the time, cosine is x and y
Okay, so,
More than that.
so, I mean, I understand where you're going, but on the inclined plane, we did the lab, right?
Mm-hmm.
This direction was what? That ended up being G sine, right, going that way? And that would be considered your X now. So I mean, just don't assume,
No,
How do you differentiate?
well, by the triangle, right? So we had the block here, remember? We had the normal force vertical and the force of gravity down. So we said, okay, there's gonna be one like this, right? So this is my FG. And this right here would be my angle, right? And this would be my cosine, and then this one right here, this one, which is that one, would be my sine. So this would be my cosine, that would be my sine. So I always look at the triangle. And the triangle changes in different problems. Other problems later on we may also have an issue. But for projectile motion, most of them are pretty much cosine.
Will the rope problem and the incline problem would be like combined?
The what problem? What problem? Rope?
Remember there was like a mass like hanging from the rope and we had to find like the tension? And
Oh,
then
you
that-
mean in the lecture?
Yeah,
That
right.
was statics. That you'll see that like exam 3 maybe.
Right, like, what I'm trying to say is that like that mass over there on the incline is attached to a rope,
Okay.
and then there's another mass on the other side of the system.
Pay attention, everybody. He's asking you guys a tough test question here. So
Right.
when I give it to you, you know to beat up.
Oh, I'm making it, alright, never mind that.
Are you not talking about a pulley question? Is that what you're talking about?
Yeah, the
That
pulley question mixed with the incline. I mean,
Yeah.
I
So
think that
he's done with the last multiple choice question, right? In the last multiple choice question, we have this platform with a mass, and then we have two pulleys, right?
Right.
Sorry, two pulleys here. And he's saying, well, what happens if this becomes an incline? It's a good question, but it's not a multiple choice question. I mean, because that's a lot more math, right?
Right.
I mean, you have to do a lot more calculation.
Oh, but that's a legit question, right? If that becomes an incline, it still works. Like,
I mean, are you asking me to ask you this question in the test?
oh, no. I'll be
I-
surprised, Dominic. Never mind, never mind. This is set up for
No, but it is a good question, and we can do that together later, if you want.
put together. Okay.
Yeah, you and I can do it later.
Better.
Huh?
No
That
one
sounds
wants to
better
do
to
it.
me.
Very good. Save that one for 202.
For 202, no, 202 is electromagnetism. 202 is going to be much harder.
Next semester.
See you guys next week.
Power goes like this, goes up to apogee, right, and then falls down. Okay. So just like we did in class, we said, okay, this is part 1. This is part 2. This is part 3. Okay. So in that case, and the reason, do you guys remember why we broke it up into 3 different parts?
It's using 3 different types of.
Because it's using 3 different accelerations. The second the acceleration changes, since in these kind of problems, acceleration is the keystone. Acceleration is really the thing that drives it. It changes between here, here, and there. Even if here and here is only changing sign, it still changes. That's why you treat it as 2 different or 3 different problems. And it's really important that you guys get that, because that's going to help you later on when we're doing more complicated stuff. So in this point here, hi, Jada.
Yeah. The reason why you kind of break it up like that, or not break it up as far as acceleration, but the diagram is we don't have any angles in there. It goes straight up and comes straight back
Yeah,
down, right?
yeah. I'm just,
But you're just
I
showing
have,
that so we
I
can
have
visually see
space
it.
to put like H max. And
Okay.
that's it. But yeah, this is a single dimensional problem.
Okay.
So it's just y or just x or just height, whatever unit you want to, or variable you want to call that
Okay.
vertical.
All right.
Right. Yeah, if it was projectile motion, yeah, then we'd be doing, probably a rocket like this, right? And then something like that, and then it would go down like this, and it'd be 2-dimensional problem. And this is more like the real rocket problem.
Mm-hmm.
And the other issue is I can't do this with you because once you get high enough off the surface of the Earth, you have to take into account the rotation of the Earth
Okay.
and the centrifugal forces on the rocket,
Mm.
right, as it's launching. So we could actually do something like that later on. I
Yeah.
think we do that in chapter, I don't know if it's exam 3 or exam 2 that you guys do circular motion. I can't remember right now. But
So we will do rocket science eventually.
do you want to do rocket science?
No.
Hey, guys, that's not a bad thing. Don't be like that.
I didn't even say.
I want to be a biologist, not a rocket scientist.
I didn't say anything.
Because it's
Well, you want to make a bio rocket?
fine. Maybe that. Maybe with baking soda and vinegar.
Baking soda and vinegar would be a chemical rocket.
True. Choo-choo.
What? I'm getting a little thirsty. You guys grab coffee and everything? For thrust, and the time of thrust, right, we said was 40 seconds. Okay? And it's asking what is the speed at the end of that thrust at this point, what's V final? And then it's asking what the maximum height the rocket will go, so that H max. So what's the maximum height? And then it's asking how long before it gets back to the ground, right? So the total time of flight. Okay? So that's what it's asking for. Now that we've broken the problem into 3 parts, right? First step is always free body diagram, right? So in this case, if we consider free body diagram, here's our rocket. Okay, so we have the force of gravity going down, and the force of thrust going up. And that's all the forces that are acting on the body. There's no, we're neglecting air resistance. And if you really wanted to do rocket science, we could. It's not that hard. You just add air resistance. If you guys actually add air resistance and the angle, that's exactly the problem that NASA solves. It's no different. Of course, you have to take into account that the density of the air gets a little skinnier, but that's easy to do. So this is the sum of so now the next step after this for part 1 is the sum of forces, right? So the sum of forces. So if we assume this is direction of motion, so this force is in the direction of motion, this is against direction of motion. So we're gonna have the force of thrust minus the force of gravity, okay? We expect that's going to be mass times acceleration. The only instance where there'd be no acceleration is if these two were equal to each other. Correct?
Yes.
You guys not too hot? You guys okay? Yeah? Okay. So if I solve this, then that means my acceleration is going to be force of thrust minus the force of gravity over mass. And we said the thrust was, what, 400 newtons?
Yeah.
Okay, so 400 newtons. And the mass was 25 kilograms?
Yes.
Okay, so 25 times 9.8 divided by 25. Okay, and when you guys did it in class, right, that A was, I think, 6.2 meters per second squared. Now you'll notice that this is a lot smaller than gravity. But it's positive. So it doesn't matter. It could be 0.001. You'd still leave the ground. It would just take a long time for you to be going quickly.
Why do we add the 25 times 9.8 again?
Well,
That's like
force of gravity, the force of gravity is always going to be the mass times the acceleration of gravity. Or its weight.
So it's all the time multiplied. 9.8 by whatever the mass is.
If 9.8 is the acceleration of gravity, I could ask you on the moon, and then it'll be 1.72. I could ask you on Jupiter. So in this problem here, we're assuming it's the Earth, which none of you asked me, by the way, but we're assuming it's the Earth, and the Earth has 9.8. When we get into circular motion and gravity, you're going to find that you can actually calculate what g is anywhere in the universe, and you'll be able to do it like easily. But right now, we're just giving a fixed number.
It's like the notation of G is just 9.8, but the notation of F of G is massive.
Well, F subscript g, so this is just, what kind of force is this? It's a gravity force. But that equals a mass times the acceleration of gravity. So this g is not subscript, right? It's just a number.
Got it.
But this g is a subscript. It's just giving it, like when we say friction, right? We say force of friction. So we say force friction, we say force pulling. We're just identifying what kind of force it is. Good?
Mm-hmm.
But you don't even have to say force of gravity. You can just say weight, right? I mean, I know in high school that's what they do. They just call it the weight. Be done.
What's the gravity is easier to remember?
especially when you have a lot of other forces, right? And then it's just all F whatever subscript. Anyways, okay, so 6.2. So this part of the problem, you know, we drew the free body diagram, wrote the sum of forces, solved for A. Excellent. Next step is the equations of motion, right? So we have, so in this case we have V final plus V initial plus AT, right? And we have Y final plus Y initial plus V initial T plus 1/2 AT squared. Now, at this point, it started from rest, so we know that V0, right, equals 0, and we know that Y0 equals 0. Yeah? Well, if that's the case, then that, of course, makes our life a little bit easier, because we can right away get rid of this guy, get rid of this guy, get rid of this guy, sorry. So now the equations become a little easier to work with. So it asks us what's a V final. So right now, it's asking us for V final. We know the acceleration, and we know the time, right? The time says it's burning for 40 seconds, so we know the time. So it means we can solve what we need to find from just this equation, right? So this is V final. And that kind of analysis where you're looking at, does this equation give me the information I need? Do I have enough information to solve it? That kind of process, you really want to get used to thinking about it when you're doing these kind of problems, right? 6.2 times 40, okay? Which we said it was V final equals 248 meters per second. So 3.6 is still really not that high, right? I mean, it's basically 1,000 kilometers an hour. It's not that high. For a rocket. Okay, so now we plug in here. So now we found this. This is what it's asking us for. So check. We found the first one, right? Okay. It's going to ask us now for H max, which means we have to go into the second part of the problem. But to do that, we want to know how high we are when we start this problem. So we have to continue with this part. So Y final, right, is going to equal 1/2 times 6.2, right, times 40 squared, right? So it means Y final, in this case, 1600, 3.1, 1600, so it's 800. It's 800 times 622.
1,960.
Okay, so this is our Y final at this point, right? So now we're done with part 1. For part 2 now, we're going to look at, of course, force of gravity, right? And that's it. There's nothing else. There's no air resistance. There's no thrust. So that means we can write the sum of forces.
Are you assuming that's in like space?
No. Why?
When you lose like
4,960 meters? It's not space. Definition of space is 100 kilometers. This is only 4.9 kilometers. And when we get to that chapter, you're going to realize that even in space, you have 9.5 meters a second squared. I mean, at the D mark 100 kilometers, you still have 4.5 something, or 9.5 meters per second squared of gravity. So, you still almost have all of your gravity still at that point. They just chose 100 kilometers. It's sort of weird. There's no physical reason why 100 kilometers is the D mark of space. It's not because gravity's gone. It's not. There's still atmosphere up there. I mean, it's very thin, right? But it's still atmosphere. And it's just so it's like an arbitrary number. It's like a unit. It's okay. Let's make it one, like a whole number kind of thing, right? Or 160 nautical miles. Okay, so sum of forces for this second part is going to be only force of gravity, and the motion's this way, but gravity's that way, right? So that means it's going to be minus Fg. Okay, that equals ma. So if I solve for the acceleration, again like last time, a equals minus Fg over m. And as we mentioned a second ago, Fg is mg, so the m's are going to cancel, right? So this just leaves us with negative g. That's our acceleration. So once we have our acceleration, we can, right? I mean, remember the step is the same. Free body diagram, sum of forces, acceleration, equations of motion. Free body diagram, sum of forces, acceleration, equations of motion. That process over and over, it doesn't change. And the same equations, right? The only reason these change is because it's based on your free body diagram. Your free body diagram allows you to identify what's acting in the forces and in what direction, and then you can just put it in right there. That's why you do that step. Eventually you'll be able to do it off the top of your head, but until then, you want to fill that step in. I mean, I wouldn't be surprised if some of you are already at the point where, okay, I see this part kind of problem, immediately I know acceleration is negative gravity. Done. You know? And that's fine, but you do this to make sure that you don't mess up on your accounting. So we have V final now, equations of motion. This is V initial plus AT, right? We have Y final, Y initial plus V0T. It's 1/2 AT squared. Okay, now we have to discuss boundary values. We found the final speed and final height at this point for this problem. But this represents the initial speed and initial height for the next problem, for the problem 2, right? This is problem 2, or part 2. So we know what V0 and Y0 are. This is now my V0, this is now my Y0. So it's called the boundary value problem. So when you cross that boundary, you just transfer the value, right? We also know something else. We know that at this point, V final is going to be 0, right? And we know it's going to be 0 y because it's decelerating until it stops, and then it starts to fall. So that's why the V final at the top is 0. So we know this guy, right? So we makes life easy. This is 0, right? Okay. Now, we also know the initial, the acceleration. We just don't know the time. So we know this guy, we know this guy, so we can definitely use this to find the time. If we look at this, we know the initial, y initial, but we don't know y final, and we don't know the time, but we know v0 and a. So by itself, we can't solve this problem yet until we solve for time. So this is the appropriate equation. And it's just by chance that the way we're asking questions, this equation seems to be the one we use first, but it's not always the case. Like in the free fall problem, this is the one you use first. And you actually solve the quadratic for the time. Okay, but in general, you just solve whichever one is the one that you can solve with the information you have. And if neither one, then look back to see where you missed something in terms of the information, because it means you missed something. Okay. So anyways, so this is now 0. Oh, stick with purple. Purple looks good. So we have 0 equals v0 minus gt. And again, we can bring this over, right? So we have gt equals v0, means our time equals v0 over g. And it looks familiar, right? You guys have seen this a dozen times. This is the time it takes to go from here to the apogee. This point, maximum height, is also called in rocket speak the apogee. Apogee. You guys would have heard it if you watch any space, rocket like launch movies. It's called the apogee. So when they say that, now you know what they're talking about. So that's the time. Now that we know the time, we can find the maximum height, right? So y max here, okay, or y final is going to be y0 plus this guy here, which is v0 times this time right here, which is v0 over g. And a is negative, so it's negative g times v0 squared over g squared. Remember we did this just a second ago with a soccer ball. So one of the g's goes away. We're left with 1g on the bottom. And now we have v squared over g minus 1/2 v squared over g. Again, apple minus half an apple leaves me half an apple. So that means my y final is equal to y0 plus 1/2 v0 squared over g. And that means you guys are going to have to calculate it now. Y initial was 4960, 4960 plus 1/2. V0 squared is 248, so it's 248 squared divided by g, which is of course 9.8. Okay? I don't know if you guys got 8,000 or something, I don't remember now. That wasn't 9,000. Can't factor out the 9.8 either in this one, so.
8,098.
Hmm?
I think it's 8,098.
8,098, yeah. Good. 8,098. Okay, meters. Okay, so basically 8 kilometers. Okay, so that's the maximum height. So right now, you know, you just found the other thing that's asking for, okay, which is the 8,098 meters. And again, the process, and this is what you guys really want to deal with, is these equations are given to you, right? So all you really have to do is remember how to draw your free body diagram if it's a simple problem. If it's a complex problem, then you have to break it up. Think to yourself, does it have multiple accelerations? If it does, break it up into smaller bite-sized pieces. And then each piece is going to have very simple, you know, free body diagram, sum of forces, acceleration, equations of motion, and your answer. And that process never changes. It's always the same, and the same equations. So it should start becoming really, really sort of clear. Okay, the last part of this is this time here represents just the time to go from here to here. And we have the 40 seconds from here to here, right? So this guy, I think you guys did it, was 25.3, whatever, so it's t equals 248 divided by 9.8, right, which is 25.3, okay? So now we have 40 plus 25.3. Now can I erase this part, or no? Because I gotta do the last part, right?
Yeah.
Yeah? That's, okay. Yeah, I don't need anything. Okay, we remember 248 was the maximum speed, so that's all we gotta remember. Right? Okay, so for part 3. Okay, for part 3, again, it's a boundary value problem. We're gonna have, was the V final for this part, is now V initial for that part. And H initial is this part, but a better way to treat the falling down part is to say the distance it has to fall is from here to here. Is that distance, right? That's all there is to it.
I have a question. Why is the total flight time not just 2 times what we already have?
Okay, twice the time it takes to go to maximum height is only for projectile motion. So from this point here to here and then back here, yes, the time it goes from there to there is equal to the time it goes from there to here.
Okay.
But we have all that distance to go to get back to the ground.
But we.
Remember, this right here, the acceleration is not gravity. That's why this time is not going to be the same. You know, that's why they're not symmetrical.
But with the given information we had in the beginning, we could have found that initial distance under thrust.
Yeah, but this acceleration here is not the same as this acceleration. You want to be careful.
Yeah.
It's theoretically, you could say I have 4 parts, right? 1, 2, 3, 4, and then say this part is just twice this time. So I have this time, this time, and this time, and then just figure out acceleration from here to there. That means you have to find the speed here as your initial speed, and then you're still doing the same steps. So you're doing it 4 times instead of 3 times. I don't know that you're saving a lot, right?
Yeah.
I mean, this asymmetry from the thrust, the way you guys can answer this question is you can have a rocket or you can have something like a cliff with projectile like this. The rocket or the cliff, it's the same problem. The only difference is for the cliff, you save yourself the initial step of calculating what the acceleration is and everything here. But the asymmetry, you know, the breaking the symmetry, that is different ways you can ask the same question. Okay?
May I ask a question? So after you did Y max, you went back to T. Is it just because we didn't plug the number at first?
This question asks us for V final, H max, and T of flight. So the reason I went back to T is because I said, okay, I answered 1 and 2, right? This is the answer, right? And now I have to say T flight, but I can't answer T flight without knowing the time. So I just plugged the number in. I mean, theoretically, you could have just never plugged the number in if it wasn't asking for the time of flight. So in this part here, we're just free falling down. Our initial speed is 0. So our acceleration, we already found acceleration is, well, okay, so if we do this guy, force of gravity is like this. But also it's falling down in that direction. So it means the sum of forces is going to equal Fg, because they're going in the same direction of motion, equals ma. Means my acceleration equals g, right? Okay, too fast. Equals Fg over m, which equals mg over m, which is g, okay? So that means now we can plug in our equations of motion. We have v final plus v0 plus at. But this equation doesn't help us because I don't ask you what the speed is when it hits the ground. Now I could. Theoretically, I could say, well, how fast is it when it hits the ground? How fast is it when it hits the ground? I just, in this question, we didn't. So I wouldn't worry too much about it. And then we have the y final minus y initial equals v0t plus 1/2 AAT squared. Now this, I just put it in this form, y final minus y initial, only because we know the distance. We already know the distance. Is this distance right here. We know the distance is going to fall, so it's just easier to put it in that form when we know it. Another way to write it is y final 0, y initial is, you know, whatever, 8,000 something something. But remember, it's moving from here to here, so it's like going like a negative distance from the thing. So you have to change the sign, right? It becomes a big pain in the butt. So just treat it like the distance. So this is this distance we already have, which is the 8,000 whatever. V initial is 0, so it goes away, boom, right? So for this equation, we have the distance it fell, right? Distance it fell equals 1/2 g t squared. And then we can solve for t, so t equals 2 the distance it fell over acceleration of gravity, and take the square root. So this right here represents the time it takes to fall from this point to this point, and that's going to be 2 times 8,098 divided by 9.8 and the square root, right? And when you guys did this last time, you told me it was 40.7 seconds. So that's great. So that means we can now answer, right? Our time of flight, right, is going to equal 40 seconds for the rocket burn plus 25.3 seconds for the projectile motion, right? Plus 40.7 for the free fall, right, which is a total of 106. And there you go. That's the last part of the question. 4 points. Now it's not hard. It's just the same steps you have to do over and over again. So it's like boring me. Suppose it's
So for A and B and C, all what we did is basically the equation of motion, and then
all you did was
everything at the end.
in every A, B, and C, you drew the free body diagram, right? Step 1. Step 2 is use the sum of forces. Step 3 is you solve for acceleration. Step 4 you plug in equations of motion. And it's always the case in Newton's laws problems. That's always the case. The homework may give you bits and pieces of it, but in general, that's the big picture. So you could do that for every homework problem. You just have to skip steps because it's not asking for this part or that part. Yeah, the second you realize this is 3 sub-problems, then that's what you did. Now, whether or not you recognize this is supposed to be 3 sub-problems is going to be how well you understand the concepts, right? Here we just identified that there's 3 different accelerations, 3 different values or directions of acceleration, and therefore we recognize there's 3 different problems. Because in Newton's second laws, acceleration is the keystone. Okay. You got a question? Yes, you do. Be honest. You good?
Last time when we did this one,
The rocket?
we had to draw it, right?
That's asking for a free body diagram. Doesn't it say for the free body diagram? So you don't have to draw the picture, the picture's for explanation.
You can draw it with the buttons.
Do you remember how I drew it when I did that problem? So is there any questions on this guy though? We're good? I know this is the hard one. You guys are done with multiple choice? You good? No more late text? Huh? No more.
Points in the positive y-axis, and then vector b is 5.5 centimeters long and points at 60 degrees to the negative x-axis, and determine the x and y components of vector a.
Okay, so this is gonna be in the y direction. And this right here is the negative x direction. So the negative x is to the left here. This is A. This is B. Okay? So. So for whenever we write these down, we have a vector A, right? Is going to be ax in the x direction plus ay in the y direction. Okay? We break it up into x and y parts. So to look at A, if it's in the y direction, 7.5, and there's nothing here, then obviously this is going to be 0 in the x direction, right? Plus 7.5 in the y direction. Can you guys see that? Because it's only in the y direction. Yeah?
So one more time.
If you look at A is just going along the y-axis. So there is no part of it in the x-axis. Or another way to think of it, this is 90 degrees, right? This is 90 degrees. So you'd have this AX would be cosine. So, okay, so we'd write this, okay, let me do it like this, maybe so you guys can use the same process every time instead of, okay, so this would be 7.5 times the cosine of 90 degrees in the x direction, right? Plus 7.5 times the sine of 90 degrees in the y direction. Now if you do the cosine of 90, you're going to find a 0. Right? That's another way. If you don't intuitively realize why there's no x, then you just do it like we normally do. Angles 90, done. So that means A equals
Cosine of 60, right, there, right?
60. No, we're talking about A.
About a. Okay.
But B is 60. Yeah, but we're not at B yet, right? Okay, so that's A. So B now, so for B, we have 5.5 is the length of the vector, right? And then this part's going to be cosine and that part's going to be sine, right? So this will be the BX part, right? And this will be the BY part. Yeah? So this will be cosine of 60 degrees, but it's in the negative x direction, so we got to keep tabs. We got to keep counting of that negative x direction. Now, if you want to do it the other way, you could also do it and say this is 120 degrees, and you'll find in the positive x direction, but you'll find that cosine of 120 is going to give you a negative number. So it's going to be negative either way. Okay? By the way it's written, you're just going to use cosine of 60 in the x direction, and then plus the amplitude or the length of the vector is 5.5, and then the sine part, the vertical part of 60 degrees in the y direction. Okay? Cosine of 60 is, I think, 0.5, so B is going to be minus 2.75 in the x direction. And I got the minus from here, and I just brought it out. So I got the minus from here and just brought it to the front. And then sine of 60 is 0.86, whatever, so it's like 4.76 y. Okay? I think that's right. You want to check with your calculator though.
4.75.
4.757 or something?
No, sorry.
Did you do it?
I got 4.75. Or 6, doesn't matter.
No, I'm saying it's like 4.758 or
Yeah.
Okay. So I just rounded it up then. That's fine, because I think in the answer sheet I wrote 4.76. So your x part is 0 for A, your y part is 7.5. Your x part for B is minus 2.75, and your y part is 4.76. So that answers your multiple choice before, right? But you see how, can you see that from there? You can't see. There's a whole seat right there. They can move their bags. Just tell them, don't be so shy. Yes, move your bags out of the way for a second. Is that yours? 5.5, right?
Vector B is 7.5 centimeters long and points at 30 degrees to the negative x-axis.
Okay, so this is B, and it's now 7.5.
Determine the x and y components of the sum of these two vectors as well as the magnitude and direction.
Okay, so this is angle 0, right? So now you can do the same thing. So if you want to do it like you did with the 90 last time, I mean, if you want to do it like exactly the same way every week. So for A, in this case, it's going to be 5.5 times the cosine, right, of 0 degrees in the x direction, plus 5.5 times the sine, right, of 0 degrees in the y direction.
And why are we doing 0 degrees?
Well, A is in the x direction. Who asked? Odyssey?
Yeah.
It says A's in the positive x direction.
Oh, okay, okay.
So if it's in the x direction and we're referencing from x, then it's 0 degrees. Now you don't have to use 0. I'm just, because Victoria was confused about the 90, I'm just showing her that it's going to come out the same. Those are practice.
Oh, never mind, just asking that question.
Okay. So cosine of 0 is 1, cosine of 0 is 0, right? So that means that A equals 5.5 in the x direction plus 0 in the y direction. Okay? And now for B, right, for B, we have the length, 7.5, and again, this is going to be cosine along its axis, so it's a cosine of 30 degrees, but it's in the negative x direction, okay? Plus 7.5, sine, it's going to start getting down, I have to do something about that. 7.5 in the y direction. Okay, so the cosine of 30 0.86, right? And the sine of 30 is 0.5. Does that sound about right? No?
Yeah.
Okay, so that's what 7.5 times 0.86. It still doesn't help much. Right? What is that? 6.5?
2.5.
Close enough. Minus 6.5 in the x direction, plus 3.75 in the y direction. Okay, so this is the x part of A. This is the y part of A. This is the x part of B. So y part of B. Then it asks for the magnitude of the addition of the two vectors, right? So, or actually, it asks for the addition of two vectors, right? X and y, right?
Some of the two.
Some of the two? Okay, so it's not asking for the individuals. Okay, so A plus B.
That's what C.
One lot. Okay, so A plus B. Remember, when you do this, it's always going to be AX plus BX. You can only add components, right? Like the X component can only add together, the Y component can only add together. Oops. Okay, so if we do that based on these numbers, right, that's going to equal AX is 5.5 and B is negative 6.5, so that's going to be 5.5 minus 6.5, right, in the X direction, plus, and the Y is 0 plus 3.75, right? So that means that the vector A plus B, right, is going to be negative 1 in the X direction, plus 3.75 in the Y direction. Well, I started out so good, now it's starting to fade. Okay, so the X part is negative 1, the Y part is 3.75.
for moving the negative out of the action?
5 minus 6.5. Well, no, 5, this is positive, right?
Well,
This
this is
part
negative.
here, yeah, this came from here. So this became negative 6.5 from that guy. But then when I add them together, it's just 5.5 plus negative 6.5. When we want to find the magnitude, the length of this guy, right? We just basically find, you know, this becomes the length, right? So a plus b, length, is going to be the square root of 1 squared. So it's 3.75 squared, which I believe is 3.88. Okay? So whenever you find the length of the vector, it's just the x part squared plus y part squared, all square root. Right? It's Pythagorean's theorem. That's how you guys should remember it. It's just, you know, a squared plus b squared equals c squared. This is exactly what it is. Okay? Because you happen to have a vector now that looks like this. This is a plus b, right? Right? So you have a vector, whenever you have a vector. Actually, I drew it too long. If I do this, I guess it'd be like that, right? So you'd have a vector that looks something like that right there. And this would be a plus b right there. That guy. And it's just a new vector. And the x and y part. And then the angle is easy. The angle is just the opposite over adjacent, right? So the angle is the inverse tangent, right, of the y part over the x part, right? The opposite over adjacent. So it's 3.75 divided by minus 1. Okay? Which I think comes out to minus 75 degrees.
Yeah.
Okay. Okay, so this guy right here is just a definition. And I can definitely give this equation to you guys if you need it. This guy you should remember, a squared plus b squared plus c squared is pretty straightforward. You know, I'll give it to you if you say, oh, I can't remember Pythagorean's theorem. But you have to say Pythagorean's theorem, no, okay.
How do you get the 75? I know I see that, but like, how do you actually get the number?
You have your calculator?
Yes.
Okay, so I'm thinking like a red car. That'd be easier, right? And I guess it's a bus.
Yeah.
Okay, so this guy is initially going speed of the bus, and this guy's initially going speed of the car. And they're both going in the same direction, right? I'll just call this the positive x direction. Okay? So when we do these kind of problems, what you do is you say, I want the relative speed. Why? Because in the problem it says, okay, they're separated, their distance, their relative distance apart, right, is 350 meters, right?
Yep.
And that's how long before they catch up? Well, the second it asks something like how long before it catches up, and all it gives you is this relative position, then you're talking about a relative problem. That's just sort of the clue. Okay? That you need to do relative speed. And it doesn't matter if they're going away from each other in the same direction but separated or towards each other. They're still relative kind of problem, okay? So in this case, then we have to understand what the relative speed is going to be. So we look at v car minus v bus. Now this is just a vector way of notating relative, okay? Is the difference of those two vectors is the relative vector, right? So this is going to give us, because we're both moving in the x direction, this is going to give us vc minus vb scalar, okay? Which is really our relative speed, okay? Now, what was vc? Vc was, what, like 24 or something?
Yeah.
Okay, so vc was 24 meters per second, okay? And then vb, the v of the bus, was in kilometers per hour or something?
36.
36?
Yeah.
Okay, 36 kilometers per hour. Now, we want everything the same unit, so this has got to be converted to meters per second. And remember, whenever we have kilometers per hour, we divide by 3.6. So 36 divided by 3.6 is easy. It just means 10 meters per second. If I'd made it 72, then there'd be 20 meters per second, so on. Pretty easy. Okay, so if I subtract the two, that means my v relative, right, is you know, 24 minus 10, right, which is 14. Okay, here we just write it down. 24 minus 10. Okay, 14 minus 10. Now that's my relative speed. So now that we have the relative position and relative speed, we look at our equations of motion. Right, one is V final equals V initial plus AT. And the other one is, everything's relative. Now, this is going to be our relative distance, right, is equal to our V initial T plus 1/2 AT squared. Now, it says that they're both moving with a constant speed. So that means what about acceleration? Zero, right? So acceleration goes away. So this doesn't give us any information then, does it? This equation is not going to help us. But this equation, on the other hand, we have the relative position. The initial speed is the relative speed, right? Times time. Then we can figure out the time, right? So we can actually give us some information. So if we divide both sides by V0, then the time to catch up is this relative distance over V0. So it's 350 divided by 10. And this V0 is literally our relative speed, right? It's our relative speed here.
Why would it be 10?
Up it's 14.
Oh, I'm sorry, 14. 14, sorry, my bad, 14, right? Which was like 25 seconds. Okay? So time is 25 seconds for it to catch up. So that's part one, right? So this is part one asking, you know, how long did it take to catch up? Took 25 seconds to catch up. And then the second part, did you want some ice for that Snapple?
Oh, no, it's good actually. Thank you.
It's good, okay.
How far from the initial position?
Yeah, exactly. How far does the car travel in that time? That's basically what it's asking. So the actual distance the car traveled is no longer a relative question. It's a specific question to the car. If that's the case, then we just use our equations of motion on the car, right? So in the case of the car is going to travel a distance, right, actual, right, that's going to be V of the car times time plus 1/2 AT squared. And on again, the car's moving at constant speed, so the acceleration is 0. Now what do we know? We know the speed of the car, we know how long it was traveling, 25, right? So the actual distance the car traveled in that time, right? Actual is going to be 25 times 24, right? Which is 600 meters. Okay? So the trick with this problem is recognizing, you know, the relative part versus the actual part. Okay? You're good? You don't look happy.
No, I'm kind of a bit sad.
What did you write underneath, delta X?
This one?
Mm-hmm. It's a little tough to read.
It's the same one, it's just repeated.
Alright, no, but what's it stand for?
Actual
Actual.
as opposed to relative. Remember in the first one we said, we basically first we have to figure out the acceleration. And the acceleration by definition is the change in speed over change in time, which is V final.
Wait, can you do number 2 before you do number 3?
Yeah, sure, absolutely. It makes sense to do that, but since no one asked me, so.
I just, like, for mine, I got negative 20 meters per second. I don't know.
Well, we're gonna have to look into that. Well, let's try it right now, right? Okay, so number 2 is so multiple choice. Number 2. So this is asking so V final is 8, V initial is 4, right? And the time is 5 seconds, right? Isn't that what it says?
Yep.
Okay, in that case, acceleration is the change in speed over change in time. So it's V final minus V initial over the change in time. So it's 8 minus 4 over 5, which equals 0.8 meters a second. So the only way I can imagine you got a negative number is you flip the V0 into V final.
Yeah, that's exactly.
You wanna be careful with that, that's gonna come back and bite you later. Okay, so that's the acceleration, which I think is all of question 2, right? Okay, so for question 3, it's a similar question, and by the way, I've noticed that people will do this in the test, they'll just assume it's the same question, but asking a different thing, so that they won't change the acceleration. You know, several people will make this mistake in the test. Assuming, of course, the question is, you know, very close to this one. Okay? Just say it, you know. What do they say? Winky face, winky. Okay, so in this case, V final, again, equals 8. V initial equals 4, but the time now equals 4. So to answer the question, it's asking how far. How far the distance does it travel? And the distance travel is going to be V0t plus 1/2 at squared. And the problem is, I want to know how far it went, right? I know what? I know V initial, I know the time, but I don't know how far, that's what I'm asked for, and I don't know the acceleration. So I can't solve it like this without doing something, right? So I have to find the acceleration. Well, it's just like we did in the previous problem. So the acceleration is V final minus V initial over delta t. This is 8 minus 4 over 4, which is 1 meters per second squared. So in that case, now I have the acceleration. Bam! So now I can solve this. So delta x equals 4 times, the time here is 4 seconds, right? That's this guy. Plus 1/2. The acceleration is 1, right? And then the time is 4, so it's 4 squared. So what do I see here? I say 4 squared plus 1/2 4 squared. Or 4 squared times 3 over 2. It doesn't matter. So 16 plus 8, right? 24 meters. Okay? So imagine in the test I switch this to 4 and that to 5. Would you guys be okay with that? Maybe you sure. So are you here just to make sure that I'm asking the same questions?
I'm here to check.
We have a learning review.
I'm doing it right.
Okay. We'll see, we'll see. So we're good? So 3's good?
Thank you.
What was hanging you up?
Yeah.
You know me? What was hanging you up? Okay, so we have a ball with some initial speed. It's gonna go up and come down, right?
Yes.
As it's going up, right now, from this picture, like you've done so many times in other problems, where's the force of gravity pointing? So where's the upward force? You know here? Force of gravity. And what's over here? Force of gravity. And when it's right there? Force of gravity.
So at what point does the force of being thrown in the air go away?
There is no force being thrown in the air. The second it leaves your hand, there is no force acting on the ball except for gravity.
So it just
Now, if
has
it
an
includes the time in your hand, then that's another discussion. Right? It's like the rocket problem. During the course of the thrust, that's not gravity anymore, it's something else. Right? But the second the thrust stops, all of a sudden now it's gravity.
So we're basically doing that, we're just not taking
Exactly. The second it leaves your hand, there's no forces other than gravity acting.
Is hitting something considered the same as applying force to it?
No, that's called an impulse. We do that next test. It's applying a force for a very short period of time.
But they're not measured the same way, right?
Well, they're different units. It's force times time. Okay? Kilogram meters per second. But there's another name for it. You've heard of it, right? The change in momentum.
I never heard of it, actually.
You never heard of the change in momentum? You never heard of momentum?
I've heard of momentum, but not the...
Not the change in momentum?
I swear to God.
Okay. No, I mean, if you heard of momentum, then it seems stands to reason that momentum can change.
There's a spider, right? It's going for your leg.
Okay? And it's going with some initial speed. And some distance down the way, we have a deer, right? What is it, 50 meters?
Yes.
Okay, what was the initial speed?
Um,
115.2
115.2 kilometers per hour.
per hour, which is 32.
Car weighs 1,000 kilograms, and the frictional force is 4,000.
The braking force.
Braking.
So the braking force is 4,000 newtons. Now it happens to be in the same direction as friction would be if it was friction. But we can't have friction by itself. We need something else other than friction. Or friction can only retard motion. But braking is different. Braking is you're slamming on the brakes, right? And you're using friction to bring yourself to a stop. So in this problem right here, we have the free body diagram, right? So here's the body, and the forces acting on this body are the braking force. Now this guy is running that way, right? So if this is my free body diagram, then the sum of all forces, okay, is going to be minus the braking force equals ma, right? So my braking force is going in the negative direction of motion, okay? So that means I can solve for my acceleration. Acceleration equals minus the braking force divided by the mass, because I just brought the mass over, right? So this becomes minus 4,000 divided by 1,000, okay? Which is minus 4 meters per second squared. So that is the deceleration rate, right, of the car, right? Or the acceleration of the car in the negative direction. So this is, 4 meters per second. So what do we do next? We always do plug it in the equations of motion, right? So we have V final. We have two equations of motion, right? V final equals V initial plus AT. We have X final equals X initial plus V initial T. It's 1/2 AT squared. Okay? And as usual, we look at the two equations and see which one gives us the information we need. The question it's asking us is the distance, right, which is the difference of these two relative positions, or the two positions. The distance is, it's basically asking, is he going to hit the deer, right? So we want to know, are we going to stop within those 50 meters or not? So we're looking for the distance. That's what we're looking for. We have the initial speed, but we don't know how long it's going to take to stop. So we don't know the time. So we're sort of screwed because we don't know the distance and we don't know the time. So this equation doesn't help us. Like this equation, on the other hand, what's V final? I mean, you're slamming your brakes to stop, right? So your V final is going to be 0, okay? And your acceleration is negative. So we can say V0 equals this negative acceleration, right, which is 4 times time, right? So time then equals V0. And when we convert 115.2 kilometers per hour, it becomes 32 meters a second. So it's 32 divided by 4, which is 8 seconds.
Again, you just divided by 3.6.
115.2 is divided by 3.6. That should be. Right? And, because remember, an hour is 3,600 seconds,
Mm-hmm.
and a kilometer is 1,000 meters. So 3,600 divided by 1,000 is 3.6. So the stopping time, the time it took to stop is 8 seconds. So now we can figure out how far, or the distance it traveled until it stopped, right? So the difference of these two is just my distance, so I'll just write it as my distance. It traveled, right? While it was stopping. Okay, initial speed, V0 times time, plus 1/2 AT squared. So this distance then is going to be equal to, V0 was 32, right? Times 8 minus 1/2. Okay, the 1/2 times the acceleration is 4, and then times the time squared, which is 8 squared. So when I look at this, this is 4 times 8 times 8, and this is 1/2 4 times 8 times 8. Again, an apple minus half an apple gives me half an apple. But you guys are more than welcome to do the whole thing in a calculator. I just like, minimizing how much I have to do. So it's 1/2 4 times 8 squared, right? Or 2 times 8 squared. 8 squared is 64, so 2 times 64 is 128. Okay, so the distance to travel for it to stop is 128 meters. So definitely the deer's, eating grill, And just a reminder, if this ever happens to you and you're sure you can't stop, hit the gas. It's the kind thing to do. I mean, your car's gonna get messed up anyways. The insurance is gonna cover whatever it's gonna cover, so you might as well just take the deer out. Not let it die slowly on the side of the road somewhere. You know what I mean?
Got ram horns though, or it was got horns, right?
Even if it has horns, by accelerating it pushes it over your car as opposed to pushing it into your windshield. It's going, because it's heavy, right? So if you hit it with too little force, it's just gonna roll into your windshield and go into your windshield, right? And those guys can weigh almost 200 pounds or more sometimes, the bucks.
So maybe if you're going like at what speed though, 45 miles per hour?
Well, it really depends on what speed you are when you're gonna hit the car. And most people don't have the luxury of calculating how fast they're gonna be when they're hitting the deer to decide whether or not to hit the brakes.
You're already going like along the road at like 45 miles per hour, 30 miles per hour, 25 miles per hour.
How far away is the deer?
Ah, true.
Because that's the thing. So if you look at it, you have a sense. If you've had to slam on your brakes in the past, you get a sense about how fast your car's gonna stop, right? If you figure the car's not gonna be moving too fast when it hits the deer, then yeah, try to slam your brakes. Try and move out of the way you can without losing control. But if it looks like if you're going, 70 miles an hour down the road or anything above 50 miles an hour, and the deer's just jumps out in front of you, don't try and avoid it. Just hit the gas and, do this kind of thing.
Oh gosh.
It's not nice, but, if you've ever seen these guys die slowly, it's not a pretty sight to.
Is it better to step on the brake and then use the?
Yes. Assume the pulleys are frictionless, no errors. One's an N and one's a 2N.
Okay. So, I should say in that picture, horizontal force, that would be a little easier for you guys so you don't have to worry about normal force and gravity. But the shaded mass is this guy right here. And in Newton forces, and as you guys know in the next chapter after the test, we're only really talking about this body. We don't care about the other bodies, but we're talking about this body and the forces acting on that body. So we don't really care about the forces acting in this guy's. But these guys are pulling the strings, which are causing tension in the rope, which are then acting on the body. So the tension is important, even though the forces acting on this guy isn't important. If that makes sense, I know it was a mouthful. So this guy has a tension force going this way, call it T1. A tension force going that way, call it T2. Has some sort of frictional force, but we don't know if the frictional force is going to be that way or that way. And the reason we don't know, right, is because the friction force is always in the opposite direction of motion. And right now, if I didn't look at these guys, I have no idea yet which way it's going to go, right? So I just know there's a frictional force, it's up. So that's the first step, right? You can forget right now about the vertical thing. So it's asking you what the forces acting on this guy are. Well, this tension here, T1, is exactly this tension here, T1, right? This tension here, T2, is exactly this tension here, T2. Okay, so this tension is driven by this guy. So if I look at this, force of gravity 1, with this guy, force of gravity 2. Force of gravity here is this mass times gravity, right? Well, this mass is 2m times g, and this mass is m times g. So that means that tension 1 is going to be 2mg, and tension 2 is going to be mg, which is now these guys. So if I just look at the forces acting on the mass, which is the first part of the question, right? A is saying I have 2mg, right? Mg, and the force of friction. That's all I know right now. Right? Next is saying the sum of all forces. Well, by definition, V the sum of all forces, right, is gonna be, let's assume, since this is 2mg, this is mg, that means this is more force than that, which means I expect it to go this way, right? So let's assume this is the direction of motion, so that means T1's in the right direction, so it's T1 minus T2, right? Minus the force of friction, because now, force of friction is gonna, we know, if motion is this way, then friction is that way. And if we just add these together, it's 2mg, right? Minus mg, minus the force of friction. Okay, well 2mg minus mg is just mg. And this sum represents the net force. So this is the net force, mg minus friction. To the right. Right? Because it's going that way. Now, if for sake of argument I did something crazy and made this 2m and that m, what would change? But this formula wouldn't change? No, it wouldn't. Because the friction would just be on the opposite side. It would just still be mg minus the force of friction. Now if I said 3m instead of 2m, or 3, then yeah, then it wouldn't be mg, it'd be 2mg. Because I removed one of the mg's. You guys see it?
Mm-hmm.
But in that second case, it's explained instead of to the right, it would be to the left. That's it. Okay? Yeah? How's it? Got quiet, you alright? Okay. So, Victoria's done? You got